Friends, this presentation takes us into a deeper understanding of how to calculate the surgically induced astigmatism through vector analysis of Cartesian coordinates and the principles of the Centroid SIA. Well, we touched the principles of Centroid SIA in my last presentation in the YouTube, but here we are going to see how this is being done, how this is calculated. Well, anything that we talk on the Centroid SIA would not be complete if we do not take the names of Nasir and Jack Holliday, who through their pioneering works during the late 90s introduced us to these concepts. Now, in order to do a vector analysis, that is apply the principles of trigonometry and geometry to refractive science, we have to understand there are certain things that differently interpreted in refractive world when compared to the geometry and trigonometric world. So one of these differences is that in geometric interpretation you have to travel 360 meridians in order to reach to the same point again. However, in the refractive world you can travel just 180-degree meridians and you reach the same point. Now, in order to remove this difference and to apply the principles of geometry to refractive science, a single angle plot is converted into double angle plot. And what we mean by a double angle plot is that each meridian of a single angle plot, that is 180-degree meridian, is doubled. So instead of 180-degree in a single angle plot becoming a semicircle, in a double angle plot that 180-degree becomes a full circle. In other words, here every 1-degree meridian is doubled to 2-degree meridian. So if you have, say, 30-degree, we would regard it as 60 degrees. So in a double angle plot, with the rule astigmatism is in the left side, and the entire against the rule astigmatism is on the right side. Well, now we are ready to apply the principles of trigonometry and geometry, because we have made the refractive world and the geometric principles, we have married them, we have made it a level playing field. What do we know about right angle triangles? We know in a right angle triangle, sine theta is perpendicular by hypotenuse and cos theta is again base by hypotenuse. We also know that the side that is opposite to the theta is the perpendicular or the y-axis, and the side that is opposite to the right angle is the hypotenuse. Now, in SIA analysis through the Cartesian coordinates, we have to take the hypotenuse as the magnitude. Now, hypotenuse is the magnitude here. This itself can be shown differently, but we are at this point of time not going into that detail, but assuming that the hypotenuse is the magnitude here. So sine theta is perpendicular by hypotenuse and cos theta is base by hypotenuse, right? So several ratios are derived here. Hypotenuse is the magnitude, right? So we can also express the y coordinate as the magnitude multiplied into sine theta. And also we can also interpret the x coordinate as the magnitude into the cos theta, right? Because simply we can replace the hypotenuse with the magnitude here. That we started by converting the single angle plots into double angle plots. So what we did is basically 180-degree does not remain as a half, as a semicircle. We have converted 180-degree into a full circle by doubling the meridian. So what it means is that if you have an astigmatic data of 30-degree, it is now 60-degree. We will interpret it as 60-degree to marry the principles of trigonometry with the refractive principle, with the refractive data. So let's start with simple data, and you have an astigmatism of one diopter at 30 degrees. How can you convert this into Cartesian coordinates? Well, we know that the hypotenuse is the magnitude, that is the one diopter here, so we can convert it x as very easily. Only thing to remember is that the axis or the degrees here, 30 degrees, has to be doubled because we have converted it into double angle plots in Centroid SIA, and so we get not 30 degrees, we get 60 degrees. So in this way you get both the coordinates, the x and y coordinates. In this way you can have all the coordinates, x and y coordinates. So let's take another example. For example, you have an astigmatic data, and from there you get an x and y preoperative coordinates, and x and y postoperative coordinates, and your SIA would be x SIA, that is the coordinate x, and coordinate y SIA would be simply subtracting the x postoperative coordinate minus the x preoperative coordinate, and then again the y coordinate, y SIA you get by subtracting the y postoperative coordinates from the y preoperative coordinates. So you get the SIA, you are only getting it in terms of coordinates, which means nothing to us in the refractive worlds. So get it back. So to get it back in terms of refractive data, you have to apply the Pythagoras theorem, which says that the square of the hypotenuse or the magnitude of the right angle triangle is equal to the sum of the squares of the sides, that is the x and y coordinates. So m square here is equal to the square of the x plus square of the y. We know the x and the y coordinates, so it is easy for us now to get back the magnitude or the SIA. The axis is through the tan theta. Tan theta is perpendicular by base, or y by x. We know the coordinates, so it is very easy to get the arctan or tan inverse from there. For your easy understanding, you can plot each of this magnitude and axis in this double angle plot. Circles would represent the diopters. Maybe it can start from 0.1 to 0.2, 0.3 diopters, and so on and so forth, and you have the meridians here. So you can plot your individual SIAs and then understand which way it is shifting, right? Which way it is shifting. So that was actually applying the principles of geometry and trigonometry to get the xy coordinates and get it back to SIA, that is the magnitude and the axis. Well, thanks for your listening, to your patience listening, and we look forward to interact more on the Centroid SIA and go much deeper than this in our next presentations.